In this video, we're going to look at constant multiples of convergent sequences and find out that a constant multiple of a convergent sequence is itself a convergent sequence. The authors of our text state this as Theorem 65. You should copy Theorem 65 into your notes carefully and then restart the video. So what we're told in this particular theorem is the following. We know that the sequence of pKs converges to x. And what we want is we want to show that the sequence of c times pk does indeed converge to cx. Now, to prove this particular theorem, we need to break it into three cases. We're going to have case 1, c is equal to 0, and that is going to be easy. Case 2 is going to be c is bigger than 0, and we're going to have to do some work on that one. And case 3 is going to be c is less than 0, and this is going to be modify case 2 to take care of the fact that c is going to be smaller than 0, and so a lot of our inequalities, they will all switch when we do a multiplication. So I want to get started in on each one of these cases. As I said, case 1 is easy. If c is equal to 0, then what I know is that c times pk, as k goes from 1 to infinity, is 0 times pk. But that's going to be a constant sequence. And remember that this is notation means 0, 0, 0, 0, 0, an infinite number of times. And constant sequences are known to converge to the constant that the sequence is. And of course that 0 is c times x because c itself is equal to 0. So case 1 is done. And now let's move on to case 2. And in case 2, we've got c is bigger than 0. And I want to kind of keep track of what it is that we know and what it is that we're trying to show. We know that the sequence of pKs converges to x. We are wanting the sequence of c times pk to converge to cx. So I want to think about what does that actually mean. In other words, what does this goal mean? So I'm going to draw a number line. Well, we're going to put cx here. And to show convergence of the sequence of c times pk going to cx, I need to slap an open interval about cx. So we are going to let s be an open interval that contains cx. And what I need is I need to trap an entail for the sequence of c times pk's inside that open interval. Now that can be a little bit difficult, so what we want to do is we want to focus in on a delta ball that lives inside S. And I can obviously draw one because this is a property of open intervals. So this is going to be the delta ball centered at Cx of radius delta. In other words, there exists a delta bigger than 0 such that this delta ball does indeed live inside the set S. And we are actually going to trap the entail of the sequence c times pk inside that delta ball. That's going to be our goal in the scratch work. And I should say this is all our preliminary stuff. How to do this. Well, the thing that I'm going to do now is I'm actually going to label some stuff as scratch work because I'm going to be doing backwards reasoning, and backwards reasoning cannot be put into a formal proof. But a lot of times we figure out a proof through the backwards reasoning. So what I'm going to say is this. I need C times Pk, well, C times Pn, to be inside this delta ball whenever n is bigger than some capital N for some capital N inside the set of natural numbers. In other words, what I'm wanting is I'm wanting C times Pn to be inside this delta ball if little n is bigger than capital N. Now, I don't know what capital N is supposed to be, but what I do know is that C times Pn is trapped on the bottom by Cx minus delta, and it's trapped on the top by Cx plus delta. So my picture is telling me that I'll get what I want. So I get what we need if we have C times Pn is trapped between Cx plus delta and Cx minus delta. Now, this is all still scratch work. And what I want to notice is that in my scratch work, I know that C is bigger than 0. So if I divide this inequality by C, the directions of these less than signs are not going to change. And that means this inequality will imply that x minus delta divided by C is less than Pn, and Pn is less than x plus delta over C. In other words, in my scratch work, I'm going to have what I get. That would say that I need Pn to be inside the delta ball centered at x of radius delta over C. Now the question is, and I want to put this in a different color, is whether or not we can reverse these arrows, because the reversed arrows will be the proof. So can we reverse our backwards reasoning? And if we can reverse our backwards reasoning, we will have the result that we need for case 2. And this here is going to be our starting point in case 2. I'm not quite done with the scratch work because I want to say one more thing about this step here. I want to note that this ball is that ball. Let me clean up my notation. That ball is an open interval containing x, and we do know that the pKs go to x. So we do know that we can trap the tail of this sequence of pKs inside that open ball. And that's also worth writing down. So in terms of a picture, if we have x written here and we look at this delta ball centered at x of radius delta over c, so this is x plus delta over c, and this is x minus delta over c, I know that I can trap an entail for this sequence, the sequence of pKs, inside that delta ball. And that's going to be very relevant when we try and turn our proof around. So now let's look at the formal proof. So the formal proof in case 2, which is C is bigger than 0. We're going to let S be an open interval containing the point Cx. And we're going to let delta be small enough where the delta ball centered at Cx of radius delta does indeed belong to our set S. Now, what I'm going to notice is this. Since C is bigger than 0, delta divided by C is also bigger than 0. So the delta ball centered at X of radius delta over C is an open interval that contains the point X. And since the PKs are known to converge to X, there is indeed a capital N inside the set of integers such that little n being bigger than or equal to capital N will imply that Pn definitely belongs to this particular delta ball. The delta ball of radius delta over C centered at X. Let me draw a picture. Here is X. Here is my delta ball centered at X of radius delta over C. And what I know about this delta ball is if n is bigger than or equal to n, then Pn lies in here. Now what I'm going to do is I'm going to think about what that says. What we now know is that X minus delta over C is smaller than Pn, and that is smaller than X plus delta over C as long as n is bigger than or equal to capital N. But C is positive, so we can multiply this particular inequality by C, and the direction of those less than signs does not change. And as a result, we get C times X minus delta over C is less than C times Pn, which is less than C times X plus delta over C. But now cleaning up our notation, we get Cx minus delta is less than Cn, C times Pn, which is less than Cx plus delta. And what this says is that if little n is bigger than or capital N, then C times Pn does indeed belong to the delta ball Cx of radius delta. In other words, we now do know that if this is Cx and this is the delta ball centered at Cx of radius delta, that C times Pn is going to be inside this ball if n is bigger than or equal to n. In other words, we have now trapped the entail of our sequence of C times pk inside the appropriate delta ball. And that lets me conclude that the sequence of C times Pn does indeed go to Cx as needed. In the next video, we will look at the final case, which is what happens when C is less than 0.